We have already discussed the process of finding out the derivatives of the various kinds of functions using different methods. And the methods which we have used, they were either you can find out the derivative of the functions using the direct formula. Then we have also used the chain rule. Then we have discussed the product and quotient rule. And after that, we find out the derivatives of the various functions using the technique of logarithmic differentiation. And then finally, we also find out the derivatives of the various functions using parametric equations or parametric differentiation. But if you look at all these methods carefully, the one thing was common among all these methods. That was what we have taken throughout all the methods which we have already used. We have taken y as a function of fx. If you remember, I told you in the very first day or in the second lecture, this is a very important relationship. We will use this relationship throughout our subsequent text. So y is equals to fx. In all those methods which we have already discussed, we have taken the function is of the type of this. And then we were getting its derivative, that is dy over dx. Right? Whatever change in the independent variable x is being done, then the corresponding change in the dependent variable y can also be noticed. So rate of change of y with respect to x independent variable is called as derivative. Now, before proceeding the next slide, our next topic, that is differentiation of implicit function. So before proceeding it, we know the function itself can be classified in two categories. One is explicit and other is implicit. Explicit function and implicit function. So the methods which we already have discussed earlier, in all those situations, our function was y is equals to fx, and this relation is known as explicit. The reason is that here we are having two variables x and y. X is considered as independent, y is considered as dependent, and x and y both are explicitly expressed. That is why this is known as an explicit function. So we have used explicit function throughout the methods which we already have discussed. Now, the second case is implicit. Implicit means anything which is not explicit is called implicit. Or you can also understand implicit means in terms of commerce, implicit simply refers to the mixture of two things in such a way that they cannot be separated again. If you are mixing two items, two commodities in such a way that they cannot be separated again, such a mixture is known as implicit mixture. For example, if you mix the water inside a milk, once water and milk are mixed together, then you cannot separate water and milk again. So the mixture of water and milk is known as implicit mixture. So in the same way, if we are having any relation of the type of such, if we are having such a relation in which two quantities or two variables x and y are related in such a way that they cannot be explicitly expressed in our earlier form like this, then such a function is known as implicit function, right? So what is the this look at this is the format of our explicit function. If we are having two variables f of x y, then if they can be written as like this, both the variables x and y are mixed together, they can be multiplied together, their powers can also be multiplied, and this multiplication and their powers multiplication should be in such a way that you cannot separate x and y from this function. So such a function is known as implicit function. In other way, you can say that if you cannot obtain this function y is equals to fx from this function, then this is called as implicit function, right? So the process of finding out the derivative of implicit function is almost verbatim. We are not going to use any new formula or any new technique, but it's a little bit different, very little bit different rather than what we did in case of explicit functions. Let us take an example. Say, find dy over dx if x cube plus y cube is equals to 3axy, right? See, here x and y, see, they are multiplied together, right? So this is implicit relationship or equation. We will find out its derivative. See, this function cannot be written as like this. Y is equals to fx. Y is equals to fx means what? All the terms of x must contain at the right hand side, and a single term of y must contain at the right hand side, right? We cannot write down this function in this form. So how we can find out its derivative? The process, the approach, the methods will remain same. We are not going to use any new methods. See, we have this equation, right? Differentiating both sides with respect to x. This is how we should write down the solution of an equation which involves implicit function. The way how to write. Find out differentiating both sides with respect to x, we get. You know, derivative of x cube is 3x square. Now, what about derivative of y cube? See, y cube, the derivative of y cube by the formula of x raised to power n is what? 3y 3 minus 1, that is 2, into derivative of y with respect to x, we will get here dy over dx. Right? Derivative of x with respect to x is 1, that is dx over dx, and if x is replaced by y, then derivative of y with respect to x will be dy over dx, right? So this is our left hand side. The right hand side is 3axy. 3 is a constant, a is also a constant. Now they will remain as it is. What is the variables? Variables are x and y, right? See here, x and y, they are the two variables and they are multiplied together. So we will find out its derivative by the product rule because this is the product of two functions. So use the product of two functions means first function into derivative of the second function plus second function into derivative of the first function. So here 3a will remain as it is. Inside the bracket we have used the product of two functions. So this is what x as it is as the first function. Derivative of the second function is dy over dx plus x y second function as it is and derivative of x is 1. So the same thing we are having here, right? So 3 and 3 will be cancelled out. See, solve this equation now. 3 and 3 will be cancelled out both sides. What is left? That is x square plus y square dy over dx is equals to ax dy over dy over dx plus ay. This ay is there. If you will open this bracket, 3ay, 3 will be cancelled out, ay is there. Now collect the terms of dy together because we want to calculate dy over dx. This is the only difference between explicit and implicit. In case of explicit, we have a single variable of y and its derivative is denoted by dy over dx. But in case of implicit functions, y may appear at more than one place. Therefore, dy over dx may be appear at more than one place. Hence, we will collect all the terms of dy over dx together and take it common because we want to find out dy over dx. To collect the terms of dy over dx together, see y square dy over dx minus ax dy over dx. Take dy over dx common, and this should be transformed to the left hand side, but left dy over dx y square minus ax is equals to ay minus x square. So the value of dy over dx will come out to be ay minus x square divided by y square minus ax. Right? So if you look at this example carefully, we are not going to use any new technique, we are not going to use any new method to find out the derivative of any implicit function. Only a little bit approach has been changed, because dy over dx in case of implicit functions will appear at more than one places. Therefore, we will collect the terms of dy over dx together and then take it common to find out the value of dy over dx. Right? Take this example. This is a very good example. See, find dy over dx if e raised to the power xy minus 4xy is equals to 0. See, e raised to the power xy, x and y are multiplied together, minus 4xy, 4 is a constant, x and y is again multiplied together. So, whenever x and y are multiplied together, in case of implicit functions, we will use the product rule to find out its derivative. So, likewise here, we will also use the product rule to find out the derivative of x and y together if they appear. See, we have this, right? We have this. On differentiation, when you're differentiating this distribution with respect to x. So see, e power xy, its derivative will be what? E power xy as it is into derivative of xy, right? We can take it because derivative of ex is what? E raised to the power x into derivative of x. This is what we have used already. So we will use same technique. X is replaced by xy. So exy as it is into derivative of xy. And derivative of xy is what? Again, we will use the product rule as we have used in the last example. So exy as it is into, this is derivative of xy. Minus 4 is a constant. Again, derivative of xy is what? First function. Derivative of y is dy over dx plus 1 into y. Now, write down its derivative also. E raised to the power xy will remain as it is. X dy over dx into plus y. This is what? This is the derivative of xy minus 4 and this bracket as it is. Now, this bracket and this bracket is same. You can take it as common. So, what you will get? X dy over dx plus y. And what is left? E raised to the power xy minus 4. So, this into this is equal to 0. Right? So, everything is clear? Now, we know from very basic mathematics that if the product of two numbers is 0, say x and y, they are the two numbers, and if the product of two numbers is 0, then this implies at least one of them must be 0. Right? So, here, the product of this and this is equal to 0. So, this will certainly imply either this will be 0 or this will be 0. So, we will take one by one. See, this implies either this is 0 or this is 0. Okay. So, take this first. If we take this as a 0, then x dy over dx is equals to minus y, right? So, the value of dy over dx is coming out to be minus y upon x. Case 1 is over. On the other hand, if the second bracket is 0, that is if e raised to the power xy minus 4 is equals to 0, then e raised to the power xy is equals to 4. Transfer this 4 from left to right, we will get this, right? Now, putting e raised to the power xy is equals to 4 in the given equation or in the given problem. See, e raised to the power xy minus 4xy, this is equals to 4. And here we are getting e raised to the power xy is equals to 4. So what we are getting? 4 minus 4xy, this is equals to 4. So what we will get here? 4 and 4 will be cancelled out. Xy is equals to 0, right? Which is not possible because If we will put xy is equals to 0 in the given equation, see what happens. E raised to the power xy minus 4xy, this is equals to 0. We are getting here xy is equals to 0. If xy is 0, what we will get here? E raised to the power 0 minus 4 into 0, and this is, sorry, this is equals to 4. This equation is 4. This should be equals to 4. So e raised to the power 0 is 1, 4 into 0 is 0, 1 is equals to 4, which is not possible, right? So from this what we obtain, if the product of these two brackets is 0, it means this 0 or this 0. We have shown that this is not equals to 0. So if this is not equals to 0, this means x dy over dx plus y is equals to 0. Therefore, the value of dy over dx is coming out to be minus y upon x. So this is how you can understand the basic concept of finding out the derivatives of various implicit functions. In fact, we are not going to use, as I have stated many times, any new approach or any new method to find out the derivatives of the implicit functions, right? This example, take this example, this is also a very much similar example. If x root 1 plus y root 1 plus x is equals to 0, then show that the value of dy over dx is minus 1 upon 1 plus x square. This is very simple. Take this. We have given root x plus y root x is equals to 0. See, this can be written as like this, right? Transform this term at the right hand side. So x 1 plus root y is equals to minus y 1 plus root x. Now squaring both sides. And whenever you know a square root is being squared, the square root is being removed. So what we will get here? It will become x square. This is 1 plus y. Here it will become y square. This is 1 plus x. Right? Now multiply this inside this x square plus x square y. This is y square plus y square x. Okay. This implies transform y square from right hand side to left hand side. So we will get x square minus y square. And this term from left to right, that is minus x square y plus y square x. So x square minus y square is equals to what? Take xy common from here, right? So x square minus y square is equals to this. Take xy common. What is left? Left x minus 1. Okay? And you know x square minus y square is equals to x minus y and x plus y. Write down their factors. So in place of x square minus y square, we can write x minus y, x plus y, and this is equals to minus xy and x minus y. So x minus y and x minus y will be cancelled out because x and y both are different, right? So what is left? X plus y is equals to minus xy. Transfer this xy to right hand side, but you will get, see here, x plus y is equals to minus xy. This can be written as y plus xy. This is equals to minus x. Take y common. What is left here? 1 plus x is equals to minus x. So this implies y is equals to minus x upon 1 plus x. Now find out its derivative using the quotient rule. You will get 1 plus x power 2 minus 1. This is how you can find out its derivative, right? So this is all about our process of finding out the derivative of any implicit function, right? Now this is all about the methods which we can use to find out the derivatives of the various kinds of functions, right? So the next stage is what? In the next stage, in the next step, we will find out the derivative of a derivative that is known as the higher derivative, right? So come to the points. Derivatives of higher order. So what does it mean? It's a very simple process. See, y is a function of x, right? We get dy over dx as f dash x. F dash x is the first derivative or derivative of order 1, right? We can again find out the derivative of the first derivative that we will denote as the second derivative. And we can again find out the derivative of the second derivative, that will be denoted as the third derivative. So the process of finding out the derivative of a function is not one stage process. It may run up to any number of stages as we require. For example, take the best example to understand this. So y is equals to x power 4, for example. See, what is dy over dx? Dy over dx is equals to 4x cubed by the formula of x raised to power n, right? See, x cube can again be differentiated by using the formula of xn. So how we will write it as d over dx and dy over dx. This means what? Derivative of the first derivative. This is equals to what? 4 will remain as it is. Derivative of x cube is 3x square. So multiply this inside, you will get here d2y over dx2, that is 12x square. So here this dy over dx is called the first order derivative of any function y is equals to x. d2y over dx2 is called as the second order derivative. See here, x square can again be differentiated. So we can find out the third, d3y over dx3, as 12 will remain as it is, and derivative of x square is 2x. So what you will get here, 12 into 2, 24x. This is third derivative, or third order derivative. See, x can again be differentiated, so we can find out the next d4y over dx4. 24 will remain as it is, and derivative of x is 1. So this is the fourth derivative, and 24 being a constant can again be differentiated. So we will get d5y over dx5 as 0. Now this process is stopped or derivation. So what this example actually shows, it shows that finding out the derivative of any function up to order 1, it's not a stopping process. It can remain continue up to any order as we wishes, as shown by this example. Second thing, if you have given a function, if you are finding out the derivative of a function, it is called the derivative of order 1. And if you are getting the derivative of a derivative of order 1, you will get derivative of order 2. And you are getting derivative of order 2, again you will get the derivative of order 3, and in so on. We can carry forward the process of finding out the derivatives up to various order, right, up to any order. And so, and then the derivatives of order 2, right, and onwards. dy over dx is not included. So the derivative from here, the derivatives of order 2 and onwards, they are known as higher derivatives. Right? We are not going, again the same thing, we are not going to use any new technique. All those methods, all those rules, what we did earlier, they will still remain process, they will still remain in process in case of higher derivatives. It's a simple example, like if you are climbing on a stairs, the first step is the first derivative, the next step is the second derivative, the third next step is the third derivative. So in this way, you can carry on your process until you are not achieving your object, right? So these derivatives are being denoted as I have shown here. See, f dash x first derivative, f double dash x second derivative, f triple dash x third derivative, f n x as nth derivative, right? So we can write it, we can find out the derivative of up to any order. See this example as we have just done. If y is equals to x cube, then find dy over dx first derivative, d2y over dx square second derivative, d3y over dx cube, that is third derivative. So simply, this is y is equals to x cubed. The first derivative is 3x square. The second derivative means derivative of the first derivative. You will get second derivative as 6x. Third derivative means the derivative of the second derivative. You will get third derivative. You can also find out the fourth. d4y over dx4 will be equals to 3. So these derivatives, meaning the derivatives of order 2 or higher order, they are known as higher derivatives. So x is equals to 80 square, y is equals to 280. Parametric differentiation we have just studied in the last few lectures. Then find dx2y over dx2 at t is equals to 2, right? See, x is equals to 80 square, y is equals to 280. Then x is a function of t, find out dx over dt, that is 280. Y is a function of t, you can find out dy over dt, that is 2a. And we know by the formula of the chain rule, dy parametric equation, dy over dx is equals to dy upon dt divided by dx upon dt. Substitute these two values, you will get it here as 1 upon t, right? Now, dy over dx is equals to 1 upon t, right? This is now a function of t. This is not a function of x. So to find out d2y over dx2, what we will get? D over dx into 1 upon t into dt over dx, because dy over dx is a function of t, it's not a function of x. So we will use this thing. So derivative of 1 upon t is, you know, minus 1 upon t square, and dt over dx is what? 1 upon 2at. Simplify it, you will get as minus 1 upon 2at cube. Now put at t is equals to 1, put here t is 1, so what you will get? Minus 1 upon 2a minus 1 into 1 into 1, that is t is 2, sorry, t is 2. So 2 into 2 into 2, 8 to the 16, you will get here minus 16a, right? T is 2, so this is your required result. Let us take one more example very quickly because time is running very short. If y is equals to x power x, then show that d2y over dx2 minus 1 upon y dy over dx whole square minus y upon x is equals to 0, right? See, we will use the same technique. We have already calculated the derivative of x power x. See, we have y is equals to x power x. We're taking log both sides, right? If you will take log both sides, you will get here log y, and this x will come here. Log y is equals to x log x, right? This we have already done. You can go through in the last lecture. After getting this equation, differentiating with respect to x, differentiate this equation with respect to x. See, derivative of log y, as we have discussed, is equals to 1 upon y dy over dx, right? This is as usual. Here x into log x, two functions are being multiplied. So we will use the product rule, that is x into log x. What you will get? X means x as it is, first function. Derivative of second function, that is log x, is 1 upon x. And then log x as it is, and derivative of x is 1. This and this will be cancelled out. What is left? 1 plus log x, right? So this is 1 plus log x. So 1 upon y dy over dx is equals to 1 plus log x. So dy over dx will be equals to y 1 plus log x. Take this as equation 1. This is what we obtained the first derivative of our equation. And what we want to show that the second derivative minus 1 upon y derivative, the square of the first derivative minus y upon x is 0. So we again differentiate equation number 1, this one, to find out the second derivative. See, derivative of the derivative dy over dx will be known as second derivative. That is denoted by d2y over dx2. Now here again, y 1 plus log x, right? This is the product of 1 and this is function 2. This is again the product of two functions. So we will again use the product rule to find out its derivative. See, 1 plus log x as it is, and derivative of y is dy over dx, right? Plus y as it is, and derivative of 1 plus log x, 1 being a constant, derivative of 1 is 0, and you know derivative of log x is 1 upon x, so you will get here y upon x. Now simplify this. What we are getting here, d2y over dx2 is equals to, see this, d2y over dx2 is equals to 1 plus log x dy over dx plus this is y upon x. So what we want to calculate or what we want to show? See, d2y. We want to show d2y over dx2 minus 1 upon y dy over dx power 2 minus y upon x. So see from this term we achieved, this term we also achieved. What is left? Here we must have 1 upon y dy over dx power 2. So look at equation number 1. What is the value of 1 plus log x from here? See, 1 plus log x can be written as dy. See, this can be written as 1 upon y, 1 upon y and dy over dx. So put the value of this from equation 1. 1 plus log x is equals to 1 upon y dy over dx. So what you will get, see, d2y over dx2 is equals to 1 upon y dy over dx into 1 more dy over dx plus y upon x. And what is this? This will be equals to c d2y over dx2. Transfer this minus 1 upon y, right? dy over dx into dy over dx. What you will get here? dy over dx power 2. Transfer this also minus y upon x is equals to 0. And this is what we want to do, right? Take, right? So this is all about our differentiation process. So students, I think I should stop it here and we will continue in the next lecture our new content. Thank you very much.